in Sustainability and Granger Institute for Engineering Faculty Scholar. She earned her BS in Environmental Engineering from Michigan Tech in 2009, her MS from Clemson in 2010, and her PhD in Civil Engineering from the University of Illinois at Chicago in 2014. Her work investigates environmental impacts and sustainability implications of emerging technologies, including nutrient recovery, closed-loop agriculture, autonomous vehicles, engineered nanomaterials, bioplastics, and alternative energy. She utilizes tools such as life cycle assessment, techno-economic analysis, and agent-based modeling to explore these technologies. She recently received the National Science Foundation Career Award to study the sustainability of closed-loop agricultural systems. So with that, Andrea, take it away.
So first, I'd like to say thank you for the kind introduction, and I appreciate the ability to give a seminar, even remotely during these interesting times at Michigan Tech. I had a wonderful experience there. So with that, I would love to talk about my work today. We'll focus on nutrients. As Professor Barkdahl mentioned, my group at Wisconsin, we work on a variety of things, largely the environmental impacts and sustainability implications of emerging technologies. And today we'll focus on nutrients and the circular economy. So we talk about the circular economy a fair amount, where we try to close cycles of materials, or in this case, nutrients. It's the idea based on industrial ecology that in the circular economy, we don't really have waste. We have products that become raw materials and feedstocks for other processes and products, and thus we keep cycling. But I would also argue that we don't only want to recover nutrients and other materials at any cost. We want to minimize our environmental impact for doing so. So we want to recover materials when it makes environmental sense and also economic sense. But that isn't always the case. And so here I have a slide talking about a Great Lake, not Lake Superior, unfortunately, but the emerging technologies to cycle nutrients. So broadly, emerging technologies, and nutrients are really critical for our survival. They're necessary for agricultural production, and I think Lake Erie is a really interesting case study just to mention this one in, because so one thing I do is I have my students read the Lorax, Dr. Seuss's book about environmental degradation, and in the original version there was a line that said that all of the animals were leaving in search of some water that isn't so smeary, and they rhymed it with, "I hear that things are just as bad up in Lake Erie." And in subsequent versions of the book, they omitted that because students actually protested it. So however, when we have too many of these nutrients that run off into water bodies, they cause eutrophication. And if we can close nutrient cycles and recover waste nutrients, then we don't have them going into the environment. And then we also don't need to source new values for these nutrients. And so new technologies and not widely adopted technologies are one way that we can do this. So particularly, we're going to talk about phosphorus and nitrogen and their issues for eutrophication, or when there are too much of the nutrients in the different waters. We need these to support life, global food production, and we'll focus on phosphorus in particular. And so the majority of phosphorus is actually mined from global phosphate rock stores, which are finite. So the question is, instead of just gathering these nutrients, using them, and then discharging them into our waterways, can we either prevent discharging them, or can we cycle them back to be used as fertilizer again and not have to harvest them from our waterways? So today we're going to consider two different technologies. The first is struvite precipitation, which was done in partnership with our wastewater treatment plant here in Madison, Wisconsin, as a way to harvest the excess phosphorus and cycle it back into the system. And then we'll also talk about aquaponics, so that's where you see like the little fish in the plants, as a way to produce food using closed nutrient loops. As Professor Barkdahl mentioned, I received funding to study that portion with my NSF Career Award. So before we get into how do we consider these technologies, let's actually take a step back and talk about life cycle assessment. So life cycle assessment is a systematic tool for evaluating the environmental impact of a product or process throughout its lifetime. It can either be just a portion of the lifetime, so it could be raw materials acquisition through manufacturing, or it could be the whole life, so raw materials acquisition, manufacturing, transportation, use, end of life, and then potentially cycling back in. And we have different International Standards Organization standards which help us set these up. But in general, this lets us think about these environmental impacts. And if you don't know a lot about life cycle assessment, one way to think about it is if you've ever heard of a carbon footprint or the greenhouse gas emissions from something, that's the same type of idea that we're talking about today. So how do we systematically look at these environmental impacts of different products and processes to make sure that we aren't just trading consequences? So for the first example, we're going to talk about wastewater treatment. And in Madison, we have some interesting issues. The first being that our water is really, really hard. So we've got the water hardness scale on the bottom. You can see that 10.5 and over for grains per gallon is like a stone. Ours averages about 18 to 20 grains of hardness per gallon in Madison. We are largely fed by groundwater. And above the figure, you can see a picture of our Nine Springs wastewater treatment plant here in Madison, Wisconsin. And so we have this issue where we have struvite, and struvite, we can harvest the nitrogen and phosphorus and make it into a pelletized prill. We also have an issue that if we don't harvest it, so we can get like these little prills that you see the hands are holding. If we don't harvest it and we don't control the precipitation, it shows up randomly. So you can see in the figure of the pipe that there's all of this deposit, which makes the pipe much, much smaller, which leads to all sorts of unwanted issues. So our goal is to not only recover the phosphorus so we can use it, but also to prevent the added operation and maintenance costs that occur when we have to remove it from there. And let's see. And so here's just where are we? You're not very far from us. So I'm in Madison, Wisconsin. And today we'll talk about the Nine Springs wastewater treatment plant, and they currently have the Ostara nutrient recovery technology system for precipitating the struvite. And so a little bit about this wastewater treatment plant. It averages about 42 million gallons per day. It serves about 300,000 people in Madison and the outlying areas. If you're interested, we have different average influent and effluent characteristics about the wastewater itself. And so what happens with our struvite system? Our struvite system covers about 700 US tons annually. And in the form of struvite, one of our biggest issues is brushite, but that has a lower market value, so that is not our goal to recover. So if we look a little bit about the life cycle assessment of this, we have a couple different cases we looked at. First, we looked at the base case. So we have our wastewater treatment plant, we have our effluent that comes out, our biosolids are transported a small portion of distance and then land applied. If we're looking at sort of the box for our assessment, we're not terribly worried about the treated effluent. We are worried about the chemicals. We also anaerobically digest our sludge, which we then use at the wastewater treatment plant itself. And another way to think sort of about the inventory analysis of what's going in and what's coming out is we're worried about we're considering the energy, chemicals, and influent wastewater that go into our base case system. And then we have the biogas, the effluent, and the biosolids. And then the transportation, well, we use our biogas for energy, and then the transportation. Our base case is the wastewater treatment plant before the struvite system was installed. So this is a comparative analysis as well as what was our environmental impact before the struvite precipitation system and what was it after. We also have our full wastewater treatment plant case study. And so this is after the struvite system was installed, where you see largely the same system, but you also have our struvite, which is trucked outside of the watershed and then put into commercial fertilizers. But in doing so, we have some differences in the chemicals we use and the quantity of energy we're using. So we can look at it the same way, where we still have our full wastewater treatment plant, where we've got the energy, chemicals, and influent wastewater. And then we have our biogas, effluent wastewater, biosolids, We use the biogas on site. We also have our struvite. And then we have transportation for both the struvite and the biosolids away from the wastewater treatment plant. So we also we're curious about just the struvite system. So what is the environmental impact of just the struvite recovery system and the transportation and considering the fertilizer offsets? And when I say fertilizer offsets, we're considering the quantity of fertilizer which wouldn't need to be produced because we are harvesting the struvite. So we have three different sort of scopes that we're looking at this with. And for a similar figure, we've got energy and chemicals. We have the struvite feed from the wastewater treatment plant, and we have the return water and the produced struvite. And of course, transportation of our struvite. So in doing this assessment, depending how familiar you are with life cycle assessment, we use the tool for the reduction and assessment of chemicals and other environmental impacts, or TRACE, which has been developed by the US EPA for a US scope. In particular, today I'll be talking about the global warming potential in kilograms of carbon dioxide equivalents and eutrophication potential in kilograms of nitrogen equivalents. And one thing to note is the nitrogen equivalents include phosphorus as well. There's some ratios sort of on the back end that they're using. The functional unit we're looking at is per cubic meter of wastewater treated. And so the functional unit is used to describe the function of the system itself. And so our environmental impacts will be all per the volume of wastewater treated. And so depending how familiar you are with life cycle assessment, there's positive and negative values. So when we look at the results, if you see a negative value, that's a net environmental benefit, it's some sort of offset. And a positive value is a net environmental cost. So here we have the results for our base case. This is before the struvite system was put into place. We've got our percentage of total impact, and we have different environmental impact categories from TRACE, from ozone depletion to, which is the OD, to GW, global warming potential, to smog, which is SM, to AC, which is acidification potential, to EU, which is eutrophication. The HHC is human health carcinogenics, HHNC is non-carcinogenics, RE is respiratory effects, ET is ecotoxicity, and FF is fossil fuel. But again, we're more concerned about the greenhouse gas emissions. And so, and the eutrophication, the greenhouse gas emissions, so here. So this is a percent of total impact. And so we've got 3.09 times 10 to the negative 1 kilograms of carbon dioxide equivalents per cubic meter of wastewater treated. We can see here that the majority of the environmental impact in this case is due to the electricity consumption. And we can also look at eutrophication potential, where the majority here is actually due to the plant effluent when we think about that there's still nitrogen and phosphorus in the water that we're discharging. We're just removing some of it. And okay, so we can look at that. And then our question is, well, we've got this full, and actually going back, you can see a little bit of the negative numbers. Those are the biosolids we're already recovering. Our biosolids are anaerobically digested and then applied on farm fields in the local area. We have our full case study where it's the same environmental impact categories, but here we have our struvite system installed. And for greenhouse gas emission, well, that shows ozone depletion, but we should be showing one arrow over to greenhouse global warming potential. Electricity is still a large portion. When we go to our eutrophication potential, we see the offsets for our fertilizer offsets for changing to, for precipitating the struvite. And so, okay, we don't see, massive benefits, but we do see some benefits across these environmental impact categories. We can also look at just the struvite recovery system, because one current criticism in the literature is it'd be great to recover this phosphorus and nitrogen, but there's a potential for it to have a really big environmental impact due to the electricity consumption. So this is just looking at our boundary of our struvite recovery system. And again, we've got our percentage of total impact, and then our numbers on the top are per cubic meter of wastewater treated. And when we look at ozone depletion, global warming potential, we can see that the numbers are red on top. That means there's still a net cost. But when we go to eutrophication potential within the green square, there's actually a net benefit to the struvite that we're recovering and an offsetting having to produce phosphorus fertilizer. And so this is interesting. But one question that comes up typically is transportation. So when we think about transporting biosolids, in particular, there's an issue with how far you have to go and the potential environmental impacts. Here at our wastewater treatment plant, our biosolids travel an average of 5 to 35 miles to put on agricultural land. And the struvite prills, or those little balls that are made, go about 357 miles. The struvite prills look a lot like if you've ever broken up expanded polystyrene. They're these like light little balls. And for us, the transportation isn't a huge portion of the environmental impact, largely because the struvite is fairly light, and then the biosolids, although they're just this wet sludginess, aren't going very far. And so when we were working on this, the primary motivation of the wastewater treatment plant was to not have this operation and maintenance issue of having to chip the struvite out of their pipes every so often. And so that was really their push. But as we were talking with them more, there was this conversation about, well, how do we think about environmental damages or the environmental damages we're avoiding by not discharging this phosphorus into our watershed? And so that led to a further collaboration with them where we had this question of what is the cost of nutrient pollution? What is the environmental benefit that can be monetized by not discharging a kilogram of phosphorus? And so we went to the literature first to take a look at these questions. And so here you're looking at a partial literature review, and this was a change in the property value per 1 meter change in Secchi depth. So Secchi depth, as I'm sure many of you know, is a measure of water quality. And so the deeper the Secchi depth, the better in general. And so here we can see that the numbers actually aren't very similar, depending on which study in terms of the change in property value. And we expected this, right? There's this question of, how do you put a price on things in the environment? And then so we were looking a little bit more into the literature. And here you'll see, this is the cost of nutrient pollution from literature calculated as loss in revenue from fisheries per nutrient pollution related event or condition. So again, there's quite a spread in terms of the monetary cost of these. So then we said, okay, we also looked at the cost of nutrient pollution from literature calculated through a loss in tourism per nutrient pollution related event or condition. So you could think about things like algal blooms or red tides, that you don't want to go swimming in a red tide. So from there, we also looked at what I think is the most interesting part of the literature is willingness to pay versus mitigation and restoration costs. And this is per kilogram of phosphorus, all in 2017 dollars. So the black circles or the blue diamonds are willingness to pay. So if you ask someone, how much would you pay to mitigate or remove a kilogram of phosphorus? And the numbers, there's a spread, but in general, they're lower than the mitigation and restoration costs. So what people are actually paying to remove phosphorus, which led to this interesting question of we've got, this large variation. And then if we took this variation and tried to somehow conceptualize it in terms of economic values, that led to more of our analysis. So from here, we totaled the minimum, maximum, range, and median of property values, fisheries, tourism, health effects, and drinking water treatment to remove this phosphorus. And so these aren't necessarily per kilogram, they're per phosphorus contamination issue event. And then we said, okay, well, how could we use this to change or influence our decision making? And so one thing we did is we pulled different min, max, and medians from willingness to pay and mitigation removal and then combined studies to say, well, if this is the cost for removing a kilogram of phosphorus, how do we factor this into the lifetime benefits of our struvite remediation or struvite removal technology? So we have numbers from our struvite system that were provided by the firm that installed it of what our system cost was and what our total project cost was. We also have the kilograms of phosphorus recovered per year, the estimated kilograms of phosphorus recovered per 20 years, and the selling price of the phosphorus, or the price to recover the phosphorus. And one thing that's really interesting about the OSTARA system and the contract our wastewater treatment plant has is that OSTARA is committed to buying back all the struvite produced. Although that does have a challenge that then Ostara tells what size struvite they would like in terms of diameter, because some diameters are more marketable. And so so we took this and we used payback period, which is, fairly simple, to say, well, if we actually include, we've got, the purchase price and installation capital cost, we have annual benefits and annual costs. And then we also could think about the struvite or the phosphorus for not discharging into the watershed and using these different source values. How does it change our payback? And essentially, we can find that our payback period would get much shorter, which isn't surprising, but we don't typically take that into consideration for our analyses. So in terms of our struvite life cycle assessment work, overall, it improved the performance from our Nine Springs wastewater treatment plant. Alone, if we looked at across all the categories in just the struvite system, it has some environmental cost or some environmental benefit, but it doesn't actually, we don't find what was feared in the literature of that the extra energy cost would just completely eradicate any benefits. And so our transportation wasn't very high, but depending on your location, that could be significant. And then if we quantify the economic implications and include it in environmental damages, it can shift our payback period. So this work was on recovering phosphorus instead of releasing it into the environment. The second project I'd like to highlight is our aquaponics work, where we're looking at closed loop food production systems. So instead of recovering the phosphorus, our goal is just not to release the phosphorus. And so what is aquaponics? Aquaponics is aquaculture, so we're growing fish in a research-linked setup, combined with hydroponics. So here is one of the ones we work with. So we have our fish that grow. We settle out some of the solids and whatnot, and the water goes to the plants, which are typically grown on floating rafts. Then after that, the water goes back to the fish. So we're using, in general, less water, and we're not losing nutrients through discharge. So here is one of the experimental setups where we've got you can see under sort of the wood area, we have our fish tanks. They're dark because these were night feeders. From there, the water goes to the clarifier, the mineralization tank, the degasser. Then it goes to our floating raft systems. So you'll see the white things with all the little holes. That is expanded polystyrene that floats on the water. And you have some rock wool, and then you have the plants which grow within it. And so this is one area we were looking into. And we were working with so there's a better view of how the plants grow. So their roots are in the water, and then when you go to harvest them, you just pull them out of the raft. And so one thing that comes up culturally in Wisconsin very much is the Friday night fish fry. And so our work has focused on producing walleye, which is not typically an aquaponics fish. Typically these systems use tilapia. In our case, we were interested in producing a fish that there's a very large market for. So this is a typical fish fry that you would get in Wisconsin on a Friday night at really any restaurant. So it's different than a lot of the warm weather studies in this area that have focused on large tilapia fillets, where we're working, our question is more about something you could deep fry and then serve with coleslaw and tartar sauce and some bread and fries. So we also applied life cycle assessment here. And in this case, when we looked at the literature of what's going on, there's not a very big agreement in terms of how you do these studies. So in some of these studies, they've looked at fish as the sole product and the vegetables are a byproduct. Others have looked at vegetables as the product and fish are a byproduct. They've looked at combinations of both, where you look at the net value or a product mass ratio. So this isn't terribly consistent. Here we used EPA's Tracy. Again, just like in the previous study, we often use this midpoint environmental assessment. And so for our system, we have our aquaponic system and we have our inputs and outputs. So when we think about our inputs or our inventory, this was heated with natural gas. We have our aqua feeds. We have the seeds for our various leafy greens. We have our water. We have our electricity, which is a mix of renewables and non-renewables. And we have our capital equipment. When we have our outputs, we have our fish. In this case, it was hybrid walleye. We have our vegetables, which were mainly leafy greens. We have our waste, so we've got our solids we've settled out, and our fish portions, which were not part of the fillet. And we can look at the environmental impact of the system using the same methods here. We've got per kilogram of fish produced. And if we looked at global warming potential, so that's at GW, we have electricity. We also have heat. This facility is located in Wisconsin, where much like Houghton, it gets very cold. And it's also very dark, and it's heated with natural gas. If we moved over to look at EU, which is eutrophication potential, we see that the fish food is part of it. And we'll talk a little bit about that more later because it's actually a really critical issue with aquaculture right now. We have our capital equipment and our heat and our solid waste. So one of our questions was we wanted to investigate a little bit more into areas where we have a really big environmental impact relative to the other inputs. And so we can't do a whole lot about heat at this facility. It's not in an urban area and it relies on natural gas. But we could look at alternative electricity scenarios. So from our electricity provider, about 37% in 2016 when the study was based is on coal. That's changed from 2005. And then we have their 2024 projections, which potentially have shifted even more since the time we wrote this paper. And so one of our questions was, how would it change if our sources of electricity change from an environmental impact perspective? And so we did a little bit of work, and we could see that, unsurprisingly, with the trends of the grid going to be less carbon intensive, we would see a reduction in the environmental impact due to the electricity consumption. We also had a question about heating. So heating was fairly high, and we can't do a great deal about it because it's natural gas in the location it's in. But this system is built in a really big greenhouse. And so there's this question of, we have our total space heating. What if we only had effective space heating? So what if we only actually heated the area we need for the aquaponic system? And unsurprisingly, we can see large reductions in environmental impact. And this is actually fairly relevant because one of the biggest aquaponics facilities in the US is actually in Wisconsin, called Superior Fresh, and they're growing Atlantic salmon and rainbow trout. And they've separated out their buildings so they can get the optimum temperature for the plants and the fish, and then only take as much room as they need. So when we looked at the aquaponics, the environmental impact changes depending on the functional units you use, whether it's per kilogram of fish fillet, per kilogram of edible plant top, or per kilogram of product. And we can visualize that a bit better, where we have eutrophication potential and global warming potential, and it looks fairly high if we're looking at kilogram of fish. And in aquaponic systems, people always tend to focus on the fish, but you produce quite a lot more kilograms of vegetables, just because the vegetables are replanted about every 6 weeks, whereas the hybrid walleye take about a year to maturity. And so this was really interesting. And then we started delving more into the area of fish feed. So aquafeed, or the fish feed in this study, it's this growing market as aquaponics and aquaculture is growing to be from about $100 billion to $235 billion for just the feeds that go into these. And it's a really pressing sustainability issue because the majority of aquafeeds use fish meal and fish oil as their sources of protein and fatty acids. And the way they get the fish meal and fish oil is they harvest forage fish, which are small fish that are harvested from the oceans. And as this market grows, there's the potential, we're actually currently over harvesting, which has a lot of cascading potential environmental impacts. And so one other issue has been the price of fish meal and fish oil has been fluctuating a lot. So it's one of the issues that is really not only environmentally costly, but really expensive for the aquafeeds and for the fish farmers themselves. The fish farmers are fairly price sensitive. There was a study a few years ago out of Johns Hopkins that a lot of these producers aren't economically viable after a few years. So they're fairly price sensitive. So one of our questions is, there's been a push in the industry right now to move from fish oil and fish meal based aquafeeds to byproducts and to other terrestrial based replacements. So like putting a lot of soy in them, which has implications on the quality of fish you produce, but also environmental implications. And there's a prevailing theory right now that fish meal and fish oil free must be better. And so this is some work we wrote where we looked at several different types of fed aquafeeds so when you have FMOCs, those are fish meal and fish oil containing. When you have FMFs, those are fish meal free. And when you have FOF, that's fish oil free. And then the green one at the end is fish meal and oil free. And so there isn't a very like distinct trend that just, if we get rid of fish meal or fish oil, the environmental impact will be inherently better. And so that was one of the interesting critical questions. And this work, one of our other questions was really thinking about something called biotic resource use. So here you see the Tracy environmental impact categories you saw before, and then you see WI, so that's water intake. So looking at the embodied water in these different feeds. And then we have biotic resource use. So that was a way of looking at essentially what we're harvesting from the oceans, because the other methods don't include that what we're harvesting from the oceans, so these forage fish are fed in the oceans, where biotic resource use looks to capture essentially what we are harvesting from the oceans or taking away from their trophic tree. And so there wasn't a clear like fish meal oil is always better, fish oil is always better. And the reason we have A, B, and C is these have to do with how we thought of it. So A is unit mass of aquafeed produced, B is unit mass of protein inclusion, and C is unit mass of live weight seafood produced. And so one thing that we did that was different is a lot of studies have hypothesized, okay, if I use this much soy, the environmental impact will be less. And we actually looked at fed studies. So these were aquaponics and aquaculture folks who tried new formulations and then fed it to the fish and compared it to what they would conventionally feed them and looked at differences in terms of like fish growth or the appealingness of the fish itself. And so we're trying to think about, how do we really analyze this? What do we do with this information? And so we tried using also the social cost of carbon, which is one way to monetize the environmental impacts. So look across these aquafeeds. And then we also calculated a shadow price for the biotic resource usage to say, okay, well, how should we think about this? How do we actually think about monetizing it? And so that's some really interesting work that we're still working on. In terms of the life cycle assessment, aquaponics provides this opportunity to close the nutrient loops in agriculture. But when we think about cold weather, we really need to think about how do we heat more effectively. Energy and sourcing influences the environmental impacts. And then we need to really think about aquafeeds as a critical issue for the expansion of these systems. So, in summary of the things we talked about today, new technology, it gives us this opportunity not only to close nutrient loops, but to increase the sustainability of our nutrient management. We can use life cycle assessment as one way of looking at emerging technologies and compare it to what we do currently. And, circularity is important, but it's also, we need to know the environmental impact of doing so because sometimes it won't be environmentally advantageous. So that brings us back to that question I had about, how do we close nutrient loops in the circular economy without spending more resources than we want to recover? Which leads us into, some of what we're working on now, because I always think that's a very fascinating part of people's research talks. So what are we doing next with this research? So the work that funded the struvite project as part of a USDA-sponsored Integrated Food Energy Water Nexus grant. And so now we're transitioning. We've looked at the wastewater treatment plant. We've also, which I didn't show today, looked at struvite recovery from dairy manure, which is a big issue in Wisconsin as we have a lot of cows, being that we are, one of the top dairy states. And now the question is, we have the environmental impacts for recovering phosphorus from wastewater treatment plants. We have a certain portion of wastewater treatment plants that are probably large enough to have this technology. We also have a lot of dairies here that are installing anaerobic digesters and have the potential to recover struvite. So how do we look at the environmental impacts avoided? How do we compare these recoveries to the environmental impact of mining phosphorus and recovering phosphorus from other sources for fertilizer? So that's one of sort of the big next questions to think about. We also have our aquaponics question. So a lot of the aquaponics facilities are small scale, they're family farm sized, and we have some larger scale ones like Superior Fresh going in Wisconsin. How do we think about that? How do we think about the economies of scale, and at what point the environmental impacts are different from our conventional agriculture? But then also, how do we truly capture all the environmental impacts of conventional agriculture? We've also, it's not on this slide, been looking at insect-based feeds more recently. So one of the issues is the fish meal and fish oil. There is a growing push by some of the manufacturers to consider insect-based feeds to replace some of that protein. And you know, it's fairly palatable when we think about feeding insects to fish versus us directly eating them, which has also been proposed recently as a way to eat lower on the trophic scale. So that's another area we're going. We've also been working with farmers to do some multi-criteria decision analysis, thinking about how do they prioritize the different considerations from environmental impact to water quality to fish production to whether it has fish meal or fish oil. So that's a lot of where we're going next. With that, you know, no faculty members in Island. And these are some pictures of my research team. In particular, a lot of thanks is due to Madeleine Sina, who is the first yellow circle. A lot of the struvite recovery work was part of her graduate work. And then Raman Gamkahar, who is the second yellow circle. A great deal of the aquaponics work has been his graduate work. And also Matt Sieb, who is our contact at our wastewater treatment plant and has been providing invaluable insight. And with that, I wanted to leave enough time for questions. Am I good on that, Brian or Dr. Barkwell?
Yeah, that's great. And let me mention too that if you want credit for education, continuing education credits for the seminar, anybody, contact Eric Seegren and he can get you official documentation. I forgot to say that in the beginning, but yeah, any questions or comments from the audience? Go ahead.
Yeah, this is Noel Urban. I had one question with your struvite work. You know, you mentioned that you included somehow the costs for reduced fertilizer needs, but it isn't at all clear what you built into that. Does that include in any way the benefit of reducing the drain on a resource that's nearing exhaustion in particular?
Oh, that's a fabulous question. So this work used an offset. So previous European-based work has said, you know, the environmental impact of producing a phosphorus, nitrogen fertilizer in these ratios is X. And we are saying that, well, for every kilogram of struvite we produce, which has the same nutrient ratio, we are offsetting that. But we're starting to work on your second question, right? So we're just looking at the environmental offsets of saying, I'm displacing 1 kilogram of this produced. Your question gets at the fact that, you know, phosphate is finite, right? And we're rapidly running out of it. And then how do we think about that from a criticality perspective? And so that's work we're starting to think more about now that we have this baseline life cycle assessment work. How do we think about the fact, you know, we're recovering a waste that would just go into our waterways versus a very finite resource? So that's next on our list, but it's a fabulous question.
Andrea, I have a sort of follow-up to that. This is Corey McDonald. So you also considered the direct environmental benefit of exporting pee from the watershed, right?
Could you repeat that? I think a couple of the words got lost.
Yeah, sorry. So in your LCA, did you also, you know, apart from just offsetting the production of fertilizer, didn't you also consider the environmental benefit of removing pee from the watershed?
So we looked at, so the struvite itself is shipped outside of our watershed. The biosolids are sprayed within our watershed. So we looked at it, if we look at like the difference of the effluent. So when you looked at, so the slides that had the environmental impact of the effluent discharged, we looked at the fact that like that is changing and the phosphorus and nitrogen in our biosolids are changing, but not at like the far reaching benefits. I have a colleague on this grant who's actually doing that. So it was a little bit of, that's a domain they're working on, but they've been working on watershed-wide phosphorus balances.
Okay. I guess, I mean, what I'm wondering about or not totally clear on is if the phosphorus recovery in the struvite essentially is reducing the P content of the MetroGrow, or the biosolids, right?
Right.
So in theory, then there's an increased need for P application by those farmers that are using the MetroGrow. So on a watershed scale, I wonder if that is just sort of a wash in terms of the environmental benefit.
So it's reducing both the nitrogen and phosphorus in the MetroGrow. But one of the issues in our watershed is we're really limited by how, essentially we have, it's a benefit when you talk to the wastewater treatment plant, because they don't have enough places to stick it. So if we reduce the amount of nitrogen and fertilizer, or nitrogen and phosphorus in these biosolids, then we can apply more biosolids to the fields and have a better place to put them.
Okay.
It's a weird problem because we also have the agricultural balance of we have a lot of cow manure. And essentially, sometimes we don't have enough places to put it.
Thanks.
Any questions from the students at all? Yeah, I was looking for Robert Handler's name in the participant list, and I don't see him there, but he does a lot of work on aquaponics too, and life cycle assessment. And I didn't know if you had ever read his work or collaborated with him. Was he here when you were here, Robert Handler?
So I gave this seminar a year or two ago at Michigan Tech, and I actually talked to some of the folks up there.
Okay.
And I think we met and talked about it briefly.
Yeah. Uh-huh. So is this feasible in cold climates, since we have to heat those buildings and heat the water for the fish, or should this be done, which would be great in the developing world, like when I was in the Peace Corps, we had this kind of idea to get the farmers to do this in collaboration with fish pond and their crops, and there's no electricity in these villages, so you'd have to do some things manually too. But do you think it's feasible in the colder climates, really?
So that's been a good question. So the majority of U.S. farming and U.S. work has been in the Southeast. So you see a lot in like Florida. The Virgin Islands had a lot with basil production for a while. And I think it's feasible in cold weather regions if, one, we insulate these systems well enough, because right now we don't. And so that's why we have such heating losses. And then also, and it's actually an issue, so the system I showed, and I didn't mention it, is in this greenhouse area, and we're growing cold water fish. So it's not warm enough in the winter, and then in the summer we have to chill the water so the DO doesn't drop and the fish don't die. So it's one of those things about more intentional design. I think one thing we have to keep in mind is we often don't conceptualize the idea of transportation and its environmental cost. So it's more environmentally impactful to produce, let's say, local lettuce in Wisconsin in the winter. But otherwise, where else are we going to get lettuce in Wisconsin in the winter? We're going to go ship it from somewhere fairly far away that's warmer. So I don't think we have the correct boundaries yet if we're thinking about this from a holistic standpoint. But yeah, I think the developing world, I mean, that's a fantastic question. I know with one of my colleagues who's been pushing edible insects that they have, in the developing world, people also directly eat insects. But there was some smaller scale things she was talking about where people were growing insects off food waste, feeding the insects to the fish, having the fish in an aquaponic setup.
There's also the social implication of would we eat bugs if we knew they were bugs? Kind of gross and disgusting, right?
So it's funny. It depends where I give this talk to. So I gave this talk or similar talk at another university, and some of the international faculty were like, "Yeah, totally, we could deep fry crickets, great." Um, and then some of the domestic faculty were less keen on it. We were writing a proposal on this recently with some partners to look at the environmental impacts of large-scale insect cultivation for aquafeeds and people feed. And as part of it, we ended up with this box of cricket granola bars. And actually, my 5-year-old saw them and proclaimed them delicious. He was like, "These are great." I was like, "Oh, I guess you're okay with it." But I think in terms of market share, people are more likely to be more comfortable with us growing insects and then feeding them the fish and then eating the fish, because they're familiar with the concept of like using fish worms to catch fish than directly eating insects.
Yeah. All right, we have a couple minutes left. Any other questions from anyone?
Andrea, could you talk, this is Judith Perlinger, could you talk a little bit about the Tracy tool and how user-friendly it is and how it is, how effective it is in comparison to other tools?
Yeah, and that's an awesome question. I just want to take a minute to say, Dr. Perlinger's class when I was an undergraduate student was the first place I had ever heard of life cycle assessment. And it was this incredible tool and this interesting eye-opening experience that I still very much use today. But yeah, so Tracy is developed by the US EPA. Most people who do life cycle assessment will use it embedded in another software. So the research standards for life cycle assessment are very much SimiPro, which has a bit of a European bent, or there's also OpenLCA, which is open source, or Gabi. And they are, if it's embedded within those, it's really simple to use. If you're using it outside of it, it becomes more complicated. We've got a project we're doing that I didn't mention today, looking at the ecotoxic effects of nanoscale silver based on the environment it's discharged into in the silver itself. And so there we're not using it within a tool. That's a little bit more challenging. But if you're using it within an established life cycle assessment tool, it's not hard to use. There's also, other environmental impact assessment methods. So the other US-based one is BEES, which was developed by NIST, which isn't terribly commonly used. But then there's also endpoint ones like Recipe, which is more Eurocentric. But I would say not terribly challenging. And there's a lot of documentation out there from Jane Barr at US EPA, who was one of the originators of Tracy.
Didn't I hear that SimiPro now has US databases? It didn't used to, but haven't they added those now? Or?
Yeah, SimiPro has, so I mean, it's still very Eurocentric. So EcoInvent is still kind of the bulk of it. But it has USLCI, the US Life Cycle Inventory from the National Renewable Energy Laboratory. But it's still missing some of it. But I had a graduate student recently who was using a newer installation where they took essentially any data that was missing in USLCI and then tried to supplement it with EcoInvent in its own database, which was a little bit interesting.
How do you have a sense for how sensitive or how much uncertainty there is in some of the results that you're getting? Because when I've done these, there's a ton of assumptions, and I don't really know what value to plug in, and I get a range and what, so can you talk about that a bit? Or?
Mhm. Yeah, and so I didn't show it, but it's in the papers that I cited that we published. So all of these, we have Monte Carlo analysis we ran on it for the uncertainty data. And then which allows us to, kind of understand where the real differences are. And then we also ran uncertainty to see, well, what has an outsized influence compared to its input. And then we can try to reduce the uncertainty around those inputs. For the two studies I showed today, these are very much like measured data. So it's not where we've mined the literature, but it's, we've worked with the wastewater treatment plant to get their chemical inventory. But I think the best way to put it is I was at a conference a few years ago, and Tom Gradle, who has done a lot of work in industrial ecology and life cycle assessment, put that industrial ecology is really a 0 decimal point field. That because there is so much uncertainty, it's not looking at the very small numbers, but like sort of the general overall comparative trends. But yeah, that's a great question that I think people are still grappling with to an extent of how do we incorporate uncertainty and sensitivity in these in the most understandable way possible.
Well, we're past our time. Anyone who has to leave is fine. If you want to hang around a little bit longer, that's fine too. But Andrea, this is the thunderous applause you would have gotten if you would have come to Michigan Tech, which it's hard to do virtually, but we really super appreciate you taking the time to talk to us. Maybe this will spur collaborations. We are very proud of you and the success you're doing since you're our graduate and you won the Career Award, which we are totally jealous about that too. So congratulations, you're really doing good.
I would just say that, none of it would have been possible without the undergraduate degree I received at Michigan Tech. I had a great experience, which gave me all sorts of research questions and ideas to pursue.
Yeah. Well, that's good. Glad to hear that. We're always looking for feedback, how to improve too. So if there's some skills you think we should be teaching our undergrads or grad students, we're always open to that too. All right, well, I guess we'll wrap it up officially. So thanks everybody for coming. Hopefully you enjoyed it. There are 4 slots left for speakers. If you know anybody who wants to speak, let me know. All right, thanks everyone.